Testing on YouTube. Testing on YouTube. YouTube testing, testing on YouTube. Testing on YouTube. Testing on YouTube. Testing, testing, testing on YouTube. Testing, testing, testing on YouTube. All right, YouTube is working. Now we got the last one to go. How's it going, Ares Aurélien? Aries Aurelian? All right, testing on X. Testing on X. Testing, testing, testing. Testing on X. Testing, testing, testing. All right, it's working on X. We're good to go. All right. Let me put this phone away. Happy Father's Day. I appreciate it. Thank you. How's it going, Sarah? MWD. This is becoming a cult. Lead us to the light. I don't want to be a cult leader. I don't want to have authority over people. Don't trust anybody who wants to have authority over you. Be an independent person. All right. I think we're going to go ahead and get started on this. All right, welcome everybody to another Hoopo stream. We're going to be doing the part 2 to yesterday's part 1. This stream is called Karpamambathy, and it's a combination of effectively 2 different repos here. We're basically taking Andre Karpathy's build NanoGPT repo, in which he has kind of a 1 Python script to train GPT-2, and we're shoehorning in a Mamba 2 block, kind of trying to do a little bit of a hybrid architecture, which is something that the cool kids are doing nowadays, and that's where the name comes from. It's Karpathy with a Mamba in between it. So we're going to be continuing on part 1. I think where we last left off was we got the training script to run. So we basically got it to run. We were having some issues with the data loader. We made a new data loader specifically for this ARC challenge. So the ARC challenge is this one. This is the abstract and reasoning corpus for artificial general intelligence. This is kind of like a little mini test that this guy came up with, Francois Chalet. It's these weird patterns that supposedly are difficult for computers but not for humans. I was actually trying to do this one yesterday, and I don't really even understand what it is. But yeah, mostly we're just kind of doing this one just because it's short. The training data set is quite small, so it's easy to train on a little local setup like we have right now. I am GPU poor, so really the setup that we've been running this on is a little bit dated, but this is a Ubuntu Linux PC with 3090 NVIDIA. It has about 24 gigs of RAM, and then you can see I have a 24-core CPU and about something like 64 gigs of RAM. So this is VRAM here, and then this is the system RAM, so like the CPU memory. All right, so we managed to get it training, But one thing that we didn't solve yesterday was that we had this bug with the Mamba. So basically, we've been trying to do this hybrid architecture where we alternate Mamba blocks and transformer blocks. And there's a bunch of different papers that we've read where people do this. For example, here is a paper, empirical study of Mamba-based language models, where they really talk about the benefit of this hybrid architecture in which you have alternating Mamba blocks and attention blocks. And even in the original, I think this is not the original, this is now the part 2 paper of the SSM. This is the guy who actually, these are the people that actually wrote the Mamba. So if you actually see this, Tri-Dow, Albert Gu, this is the same people here. So if you go to the actual Mamba repo, there's Tri-Dow, there's Albert Gu. So these are the people that actually wrote this implementation of the Mamba 2 that we're using. But they also mention this. So here, they have a whole section on hybrid models, and they talk about, they have their own little tricks for it. And one of the things we're going to be doing today is kind of starting to take some of the advice in this paper and then use that to perform a little bit of a hyperparameter sweep. But we were running into an issue with our Mamba 2 block, and we were getting this kind of cryptic error that was hard to debug. And I ended up finding it, so we're going to kind of start with that. This is the error. Runtime error, causal COM1D with last channel layout, required stride, blah, 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 to be multiples of 8. And we were like, okay, what the fuck is that? So I put that into Google, and I found this issue. Pretty convenient. Okay, so you got some guy here. He's basically running into the same thing. You see some Chinese characters, so this is like some Chinese guy here. Blah, blah, blah. Also encountered the same problem 2 weeks ago. Okay, you might try this. Okay, I was like, all right, maybe not. Let me see. Let me keep scrolling. Same problem. Anybody solved it? Blah, 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 blah. Keep scrolling, keep scrolling. Keep scrolling. Oh, what about this? You can skip causal COM1D, comment out the causal COM1D. I don't really want to do that because the whole causal 1D conv, that's actually part of the reason it's fast, right? Because if you remember in the repo here, they actually tell you that causal COM1D is an efficient implementation. So we don't really want to get rid of that because that's going to be where the speed comes from. Okay, so let's keep scrolling. Let's keep scrolling. More people talking about the problem, and then boom, you get to here. Just make sure dmodel times expand over hendim equals a multiple of 8. Okay, and you see here how this has a bunch of thumbs up and little smileys. When you're on these GitHub issues and someone has your problem, and then you find a version or you find a comment here that solves your problem, and this is what I did. So I basically took these dimensions here, dmodel, headdim, and dstate, and I made sure that this condition holds, right? So dmodel times expand over headdim should be a multiple of 8. And I did that, and it solved the issue. So thank you, Katal Pa and Xiao Shan, for this. And now that this works, and this is the important part here, guys, make sure to react with some emoji. So we're going to give this guy a little launch emoji as well. And this isn't just to make them feel good with some social reward. This is also just a way to contribute to the community, right? Because next time someone finds this error and they find this issue, they're going to scroll through this thing and they're going to look for the comment that has all the little emojis on it. So if one of these comments solves your problem, make sure to put these emojis on it so that someone in the future can go and just scroll to the one comment that has all the likes, and it's going to make it very easy for them to solve this issue. So that's how you contribute to the open source community, by just being a lurker. You know, I didn't really make a post here, but by liking these things, I will help someone in the future to find these comments faster. All right. So how's it going, Oma? MWD with a question. Tell us more about the horn thing. So this horn is called a spiral didgeridoo, which I think is a didgeridoo is basically this, but like a very long tube, and I think it's a Aboriginal Australian instrument. And then at some point, someone figured out that you could basically make it into a spiral you don't actually need it to be long and straight. So, I don't know. I just figured it was a good way to kind of announce the start and the end of the stream. Adds a little element of fun, but there's really isn't much more of an origin story on that. I literally bought that off Amazon for like $20, so it's not even, there isn't some cool situation where someone gifted that to me and it has like this whole backstory. It's not. I just bought it on Amazon. I had it beforehand. No. I have some other wind instruments that I've played. I have like this like shofar horn, and then I had this Aztec death whistle. I was like, I kind of went into it and like I bought a bunch, but none of them are as good as this one. This one is by far the coolest to play and kind of sounds the coolest, so that's the one that I'm using. All right. Let me see. Where do we go from here? Okay, let's go into some weights and biases here. Let me also spit out this gum. All right. So now that we have this training, right, we kind of need to do what's called experiment tracking. Experiment tracking is basically creating plots for all the stuff that was printing out, right? So if you remember when we're running these, you get all these basically printouts, validation loss, training loss, like a bunch of numbers. It's really hard to read that in a log like that and really know what the hell's going on. So you kind of need to plot these. There's a lot of different ways to do experiment tracking. TensorBoard is one that I've used for a long time, but also weights and biases is kind of a very popular one. Weights and biases is a SaaS product, so it's a software as a service, and it kind of is the industry standard. And it's not necessarily the best, right? So the thing with weights and biases is it's kind of like AWS, right? AWS or any other cloud service provider, the product kind of sucks, right? Like AWS, lots of little buttons, it's bloated, there's a million different things, you don't really need half of these things, but it's still the best when it comes to cloud stuff. Maybe not, there's probably some other ones now, but weights and biases is similar. It's kind of a shit product, but you really don't have that many other options, and it's pretty good, you know? So even though it has a bunch of problems, it's still kind of convenient and the best one. If you're just running stuff locally, you could probably just use TensorBoard, but if you're going to be in a team, I would recommend Wanbi. So I went ahead and added just a couple things here that you need for Wanbi. You need to basically import it. It's a pip install, right? So you can see how I've added it to our dependencies here. You add it to the conda setup, right? In our README, we have a little blurb here so that someone else can very easily copy paste it. You see how I'm pinning the version. And I also added it to our Docker file. So here's the Wanbi in the Docker file, and I had to add a specific version of protobuf to make it work. So whatever protobuf version came default with this container, or maybe it's being installed by one of these things up here, I had to basically overwrite it with this one. Okay, so now that you have that, another thing that you need to do is at the very beginning, you need to basically Wanbi init. And Wanbi init is basically telling you start some kind of run, and we're telling it a project and then an entity. So the project is going to be this. You can see how this is my kind of entity. Then within that entity, I have projects, and then within these projects, I have runs. So every single one of these is a run that I did overnight, right? And these runs, you don't just want to run the same thing over and over again, right? Because it's just going to give you the same result. So I wanted to do a little ablation here where we try with this hybrid mode and without this hybrid mode. So the hybrid mode is a toggle, and you can see here if we have a hybrid mode, it's just going to be a bunch of transformer blocks, or if it's not the hybrid mode, it's just a bunch of transformer blocks, and if it is the hybrid mode, it basically alternates transformer and Mamba blocks. I also had a different seed. You know, sometimes you want to change the seed just so you're not doing the same exact thing. I didn't actually do an ablation on the max steps, but one of the things that we're going to do later today is add more things here, right? Because what we're trying to set up for tonight is a sweep where we're going to be sweeping over a bunch of different hyperparameters and seeing which one works better. And this is a pretty standard thing to do here. I have here, for example, in this paper, so let me see if I can find it. Maybe it was here. Yeah, we performed some studies at smaller scale and found that Mamba network hyperparameters are similar to that of transformers, and as a result, we use the same hyperparameters across models to make a rigorous direct comparison. So what people do is that when you do these types of sweeps, right, you're effectively running this entire script with a very specific set of hyperparameters. So this is a hyperparameter, this is a hyperparameter, this is a hyperparameter, and we're going to add even more of these by the end of this stream. But every additional hyperparameter kind of explodes the search space, right? So you have to try basically this is going to multiply your search space by 2 because every single configuration you have to try with and without the hybrid mode. We're going to add a hyperparameter for the percentage of Mamba blocks versus transformer blocks. So you can see how the search space gets very big. And if every single evaluation that you run or experiment that you run takes extremely long because you're using a very, very big model, you're not gonna be able to sweep effectively through this space. It's gonna be extremely expensive to do so. So generally what people do is they perform these sweeps or studies at a smaller scale. So they use a smaller version of their model to sweep over the hyperparameter space and find the configurations that seem to work the best at the small scale. And then there's a little bit of an assumption that, okay, we found the perfect set of hyperparameters for the small scale. Now let's increase the size of the model and actually run the big training run version of this. And this is pretty much what everybody does. So we're going to kind of do that as well. Question from AM. Does Mamba 2 have residual connection and norm built in? When I tried connecting Mamba in sequences, it went into NaN until I added them. I know Mamba 1 has its own block for residual and norm. Okay, so what AM is asking there is a pretty good point, and basically, let's see if we can go to a Jamba model, or actually even better, let's do the attention is all you need. So let's go to this one here. So what AM is basically talking about is how these, the block that we added, for example, the transformer block right here, you see how it has this norm thing here? Usually this is actually in the front here, but actually it might be easier to show in the code because I think Karpamambathy has it explicitly in there. Yeah, here you go. So you see how you have your self-attention block right here, but then you have these layer norms, right? You have a layer norm before the attention block, and then you have a layer norm before the MLP. So is that there, right? So if we look at this Mamba block, does it have the layer norms? So let's see. If RMS norm, self.norm. Okay, so there is an RMS norm there, but it's behind this toggle. Let's make sure that that is activated. RMS norm, RMS norm, RMS norm true. Yep, so the default value for, or the default setting for this Mamba 2 block is to have the RMS norm equals true. It does seem like there's another one here, norm before gate. So let's see what that one turns on. That one turns on this right here, norm before gate, right there. I don't really know about this one. So generally with these type of things, you don't really want to mess too much with these settings, right? Like the settings that are there by default that were picked by specifically Albert Gu and Tridao, like just kind of trust them, right? Trust a lot of these settings. The more you start messing with these settings, you can end up in a place where it doesn't work at all. So it does seem like we have normalization inside this block. So we're using RMS norms, so we're just going to trust that. Okay. For release Mamba 1, the block with normal residual is Mamba SSM block. Original transformer in Karpamambathy uses block with residual connections and norms. Yeah, the residual connection is here. So this is the residual connection. You see that? A residual connection in blocks looks like this. You see this little arrow that goes like this and then feeds back up. So this arrow is kind of skipping around the block. So this is sometimes called a skip connection or a residual connection, right? And that looks like this, where you're taking this input X and you're feeding that input X into your attention block, but then you're also letting it go around the attention block, right? Same thing here with the MLP. You have the input is actually going into the MLP. You see here the layer norm. It gets layer normed first, and then it goes into the MLP, and then you still have it going around, right? So you basically, this norm is before. It goes into that norm, then it goes into the attention head. This is a cross-attention head, so we don't actually have that. We have self-attention heads like this one. And then you have this residual that goes around it, or skip connection. So does the Mamba have a skip connection? That's a good question. Let's see. Mamba 2. Let's click on Mamba 2 again. Let's go to the actual forward. There we go. Here's the forward. Boom, boom, boom. This one looks, it's a little bit more complicated of a forward. Let's actually make this a little bit bigger because it's kind of hard to read here. Let me also adjust this microphone so I'm not like leaning into it. Okay. Causal conv 1D. Self out. SSM state. Dude, this is really difficult to read. Let's see if we... I'm trying to see if I can find... Okay, so where is the actual input? Maybe we can do it that way. So U is the input, I suppose. Batch sequence U, self.step U, in projection U. What about this? In project, or ZXBCD. ZXBCD. Mamba split 1D scan combined. I don't know, guys. I don't actually know if we have a skip connection here. Let's see if it's in the paper. So if we actually go to the paper, we can see the block diagram that they have, and if there's a skip connection there, we can probably assume that there's one in the actual so we're using I think this second one, Mamba 2, is Mamba 2 block simplifies the Mamba block by removing the sequential linear projections produced at the beginning of the block as a function of the SSM input. An additional normalization is added as a norm former. So here you have a normalization here. But it doesn't really necessarily feel like there is a skip connection here. It just kind of goes straight in. Let's see. Residual, if we search for that. Residual normalizations are repeated on the same input. Uses the same residual and normalization. What if we type skip connection? Skip the hidden states and compute the final hidden state. Okay, I'm not entirely convinced here. I think if anything, I'm even just a little bit more confused. I don't exactly know, but we'll put a little to do there, and then maybe we'll go back to it and we'll add it as a hyperparameter. So let's add a little to do here. Skip connection. Or residual. We'll put that in there. Thanks, AM, for pointing that out. It's almost established now that norm plus residual plus norm is a rotation unit vector, so must have. The only thing in Mamba that is the hidden state is only latest in attention, not all history. Okay. What is the path with the only sigma sigmoid sign? All right, you guys are like deep into this right now. But wait up. We're getting too deep in it, because what I really wanted to do is to show you guys WANB, and I showed you guys that, and really the only other thing we had to add here was, let's control F1B. So now we're also adding this, right? So basically anytime we had this print, rather than just kind of printing it here and then adding it to the log file. So this is what Karpamambathy was doing. In Karpamambathy's style, he doesn't use WANB, he doesn't use TensorBoard, he just directly logs it to a text file. So you see here, here's the text file, and then he parses that text file into a Jupyter notebook and then plots it with matplotlib. So that's probably the most primitive way you could do it. I try to avoid matplotlib as much as possible just because it's old and crusty and trash, even though it's very good. But you see here, you just add that WANB log, you add that WANB finish. We also have another WANB log here, so this is going to be the validation loss, and then you have the training loss. Okay. So once you do that, and we sweep over our stuff, we're going to get these runs, right? And we have all the different stuff that we were logging here. We have our validation loss, and we have our training loss. So right away, we can see that our training loss goes down, which is good. It's a little bit weird, and you have a couple different things here. And it also, you can see we're kind of overfitting, right? So when I see this, it basically means like we just overfit to this training data set, which makes sense because it's really small, right? So if the task, it's just 400 tasks. They're all inside just this one Git repo, and we basically overfit to it, right? We also have the validation loss here. So the validation loss doesn't quite, you see the lowest it gets here is about 0.5, right? And the reason you can't get to a literally 0, which I think is what this was, what did it get to? It's got to like 0.06, right? So 0.06 on the training loss means we overfit hard to it. But then you can see here how actually this is another indicator of overfitting, is that here your validation loss is about 0.3, and then it started to go up. So now it's about 0.5. So when your training loss continues to go down, but your validation loss goes up, that means you're overfit to it. Here's another little piece of something you could do. So you can see here how some of these failed, some of these got killed. So one thing that I like to do here is I always like to clean these up. So I come here, I'll just take the ones that select these. Let me also take these ones here. You see how this is 4 seconds, 5 seconds. Those are basically bullshit runs that never did anything. So we can click all these ones that are like 12 seconds, 11 seconds, 11 seconds. We don't want any of those. 38 seconds. We do want these. 19. So 38, 5, 4, 6. And we're just going to delete these. Also delete the artifacts. Okay. Hit refresh. And now we just got the runs that we want, right? So each of these runs was roughly an hour. And you can see that some of these have the hybrid equals true, some of these have the hybrid equals false. Slightly different seeds, but pretty much everything else was the same. So let's go back to the workspace and we can kind of compare these. All of these were kind of the same. It's really difficult to say whether any of these is better. They're all basically doing the same thing. So it seems like with Mamba blocks, without Mamba blocks, doesn't really matter. This data set is so small and the model capacity is quite big, so it just kind of overfits. But I wanted to test something out here. So I'm going to take a screenshot here of this, of the validation loss and the train loss. And the reason I want to do that is I want to compare GPT-4o and GPT. So here we're going to paste that image there, and we're going to say, here are the training and validation loss curves for my model. What can you tell me? Oh, fuck, I overwrote the screenshot. Let's take another screenshot. Boom. Copy, and then we're going to go into here. And this one's going to be GPT-4, because one thing that I've heard is that GPT-4o is fast, but it's not as good when it comes to programming. So I wonder if it's going to not be that great. So we're going to do this, and I want to kind of compare their ability to look at curves. So we're going to do GPT-4o, and then we're going to do GPT-4. See which one is better. Okay. Training shows several key points. Both the training and validation loss decrease significantly, indicates the model is learning. Okay. Very close to each other and follows similar trend. The model is not overfitting to the training data, which is a good. Overfitting typically occurs when the training loss continues to decrease, but the validation loss actually increases, which we did see. You know, it's kind of happening right here. It goes from about 0.3 to about 0.4, so that did happen. I think it's just too small for the model to really notice that, right? Because it's kind of a little tiny JPEG here, so, or PNG. Plateau towards the end. The model has reached its optimal performance. Steep drop indicates the model quickly learns. Model is training well, blah, blah, blah. Okay. Kind of average, you know. Let's see what GPT-4 says. Model converged. Lack of spikes suggests that the learning and other hyperparameters are set appropriately. Closely tracks, good sign. There is no apparent divergence. Around 600 steps. Ooh, that's actually kind of interesting. So it was able to OCR. So generally when you're feeding images into these vision language models or multimodal language models, right? Like they're not great at OCR or optical character recognition for little tiny little text like this, right? So I'm actually kind of impressed that it was able to read the number 600. And interestingly, you see this one did not read that. So this type of vision language model, right, what it's actually doing is it's cutting this image usually into a couple different images, and then within that it feeds that into an encoder, which is usually a vision transformer, and that type of encoder will then patchify this image into little tinier squares and then feed that into a vision transformer. So what this tells me, the fact that GPT-4o did not mention the step, means that it probably didn't actually read any of this text. So it makes sense to me, because what it tells me is that GPT-4o is probably intended to be fast, right? So it doesn't really need to have a very high resolution view of the image. So it's probably just cutting this and getting the general gist, versus GPT-4, this one is probably more trying to really, really get the best possible performance. So it is using a bigger VIT that has more patches that allows it to kind of see the actual text. So overfitting is not occurring, or at least not significantly. Okay, that's a little bit better. Towards the end of the curve, both the training and validation plateau. The model has nearly reached its capacity under the current configuration. Further significant reductions may require adjustments such as more complex and more data. This is really, I think, the more important part here. Because to me, the TLDR from this that I'm getting is that it's basically the data is not very difficult. This isn't like a difficult problem. Okay. Stable and effective. All right, that's pretty much good. I think we kind of got what we wanted to get out of that. What is the path with the only sigmoid sign? Okay, you guys are still talking about this Mamba here. Let me answer the other question. I have an experience in recommendation systems and now want to learn LLMs. What is the best approach? Replicating research papers, building projects, any recommendations? Yeah, I don't think that it really matters, you know. It's just kind of do what is most interesting. Like there's an illusion that if you do something more, if you learn in a more optimal way, you're going to somehow get to expertise faster. But it's not really it's kind of like a marathon, not a sprint, right? The only way you're going to get to expertise in anything is just doing it over and over and over again. So if you force yourself to try to learn in a way that's not fun to you, then you're going to give up. So almost the most important thing that you want to do is make sure that whatever process you're using to learn, whether it's trying to implement papers, or whether it's just reading papers, whether it's doing little side projects, just pick something that is fun for you to do so that you continue to do it. And then, you know, years will go by, and then eventually you're like, oh, holy shit, I feel like I'm kind of no longer a noob. So pick something that is fun. Wanby uses random sampling for performance reasons if there's too much data. If graphs are close to each other, it doesn't even matter much. Yeah, Wanby is a little bit sketchy. There is some stuff like that. I don't know if it's literally picking random numbers here. That would be really fucked up if it did that. But like I trust that this is actual numbers here. Right? 0.3, 0.2, 0.2, 0.5, 0.5, 0.5. What's your opinion on Grok and its fast inference speed? Grok is a company that produces chips. It's like a startup specifically for inference. And we've talked about this before, but I think it's likely that you see a divergence in the hardware, right? You'll start to see hardware that is specifically for training, and then you'll start to see hardware that is specifically for inference. And Grok is proof that you're going to kind of start seeing that, right? And I don't know. I feel like it's probably good, you know? Like, I don't know if I would necessarily buy stock in them myself because, you know, you have companies like NVIDIA. NVIDIA is really good at, it's basically the state-of-the-art hardware for training, and it's kind of the state-of-the-art hardware for inference as well. Maybe Grok is good for specific applications, but if NVIDIA, at some point, right, everybody right now wants to train AI models, but I think in the future, these foundation models are going to be so good that the majority of the compute is actually going to be inference, right? Right now, it's like most of the compute is training, and then you have some inference amount, right? Because everybody wants to train their own models. But give it a couple more years, and I think people will stop training their own models, right? This idea of like some random little startup making their own model will seem kind of stupid because the foundation model that is trained by one of these big companies will be so much better. So at that point, there will be more of a demand for inference hardware as opposed to training hardware. And when that world comes, I'm pretty sure NVIDIA will quickly become the best at that as well, right? So NVIDIA might be like, okay, we spent a couple years making very, very good training hardware for the big players. Now the big players kind of don't want any more training hardware. What they really want is this inference kind of hardware. We're just going to do that as well. And whenever they start doing that, you know, maybe the people who bought a bunch of Grok chips, they'll be like, hey, you know what? The next kind of data center that we have for inference purposes, maybe we just buy NVIDIA chips instead. So, I don't know. I'm kind of just predicting the future there. So 50-50 chance it basically doesn't actually happen. But how do you structure your work? How do you decide on which topic you will work on? I'm feeling lost and I don't know how to approach my learning. I just like, I don't worry too much about like what I work on. I just kind of like let my lizard brain pick what I find is interesting, you know? So like, I don't know. I thought the Karpamambathy video was kind of cool, and I kind of liked Mambas as well. So I was like, why don't I just join them together, right? There wasn't much extra thinking behind that. There wasn't like some 500 IQ like decision where I was like, this is going to lead to the job or something like that. I just kind of like arbitrarily picked it. And why did I pick this one? Well, because I just happened to listen to a podcast with Cholet. So I was like, oh, why not? Let me try it, you know? Preparing for interviews, I asked DSA and PyTorch of self-attention. So much to learn just to crack Gen AI roles. Grok chips are old, 15 nanometer. Yeah. They're using older stuff. So all of these chips, whether it's NVIDIA or Grok, they're basically made by this Taiwanese company, TSMC. And you can think of TSMC as basically the printer. And TSMC doesn't even make their own printer. They buy it from a different company, I think called ASML. Yeah. So there's every generation of printers basically prints smaller and smaller and smaller. So whenever people talk about like, oh, the 15 nanometer process, right? Like they're basically talking about kind of the generation of printers, right? So you can see how slowly over time it's going down and down and down. So you can see here, 1990, we were at 600 nanometers, then 65 nanometers, 14 nanometers, and now in 2022, we got 3 nanometers. But they don't have, not all the printers are 3 nanometers, right? Only the like cool printers, the like next generation printers. So TSMC has very deep relationships with a company like NVIDIA. So NVIDIA is going to be the company that gets access to these 3 nanometer printers, right? If you're a company like Grok, they're not going to give you access to the 3 nanometer printers, right? Because the TSMC is like, new phone, who dis, who the fuck is Grok? Like, you don't give us a ton of money. We don't even know if you're going to be alive. So you guys can use the 14 nanometer printers, right? So Grok created a fast inference chip, even though they're on an old technology, because they designed the hardware specifically for that task. So that's how they can get something that's very fast on inference, even though it's technically using kind of outdated printer. I'm calling it a printer, but it's actually much more complicated than that, right? It's like immersion lithography, right? There's a YouTube video that I recommend for this. It's YouTube how transistors are made. Let me see if I can find this, because this video is fucking amazing. All right, I'm never gonna find it. I'll post it on the Discord, but there's this YouTube channel that has like really, really nice animations that show how all these things are made. But yeah, I mean, imagine if Grok was able to get access to the 3 nanometer line. You know, that would be really, really good. They would probably have state-of-the-art inference computer, but the problem is they're not going to get access to that, right? Because they're just a small little startup, and NVIDIA has been working with TSMC for long enough that they're the ones that get access to the cool stuff. Will I be doing more coding streams in the future, just like this? Kinda, yeah. I mean, if you guys like it, I don't know. I like the paper streams just because it's like, it's pretty cool. Like, I think reading papers is a little bit more fun and one-off, right? It's like the problem with coding projects is that you need to put so much more time in before you get anything interesting, right? It's like a lot of coding projects, you're just sitting around, just kind of like messing around in Python. It's like, it doesn't really feel like I'm learning as much as like whenever I read a paper, right? It's like a different kind of learning, but to me, the paper is more fun, right? It's like you get to kind of, I don't know. It's hard to describe, but I think paper reading is more fun. It's also easier, right? You're just kind of like reading a paper. You don't really need to necessarily understand it that deeply. You just kind of like, wow, that's kind of cool. And then that's it. And then you never look at that paper again. Versus the coding, it's like you spend a lot of time just sitting here, just like fiddling with Python, and then get to something that isn't even that cool. Why not both? That's the real answer, Brian. I think you have the right idea. All right, you guys have a lot of questions here, but I feel like questions are more cool, right? What do you do for a living? I do this kind of stuff. So I'm a software engineer in the AI world. Samba Nova Systems is another company that has the same inference speed. The fuck is this? Samba Nova? Samba Nova Systems? Revolutionize AI workloads. Samba Nova. Accept. Give me your cookies. Enterprise integration. Oh, look at that. You can drag and drop it. Perfect. Exactly what we need. All right. Let's learn more about this. So, Samba Nova Systems, let's do Crunchbase. Crunchbase lets you know when they were founded, kind of their funding rounds. So we can go here to financials. So we see their seed round was in 2017. Come on. Crunchbase used to be cooler, but now they kind of they lock this data. But you can see they're raising a bunch of money. They started in 2017 with a seed round, and they're on their Series D right now. Palo Alto, so Bay Area company. Christopher Rodrigo Leong. I don't really necessarily know these people, but cool. I mean, I don't know if they have access to if they have a really good personal relationship with TSMC and they get access to the good chips, maybe they're cool. But also, here's another dark horse. I had a stream on this as well, but extropic and normal computing, like, this is almost like if Grok and Samba Nova are like the startups that are working on inference chips, these guys are the startups that are working on the training chips, right? We read a paper where these type of probabilistic or thermodynamic computers are actually very good at calculating second order gradients, which means that they can potentially result in faster, better training. So there's a cool world where all the training for big models is done using these types of probabilistic computers, and then all the inference is done using kind of just standard silicon that we have now, right? So that would be kind of a cool world where you have literally the technology that is used for inference versus training is different. It's a different tech stack. Right now, it's the same tech stack, right? You're kind of fundamentally using the same type of chip for training that you are for inference, at least when it comes to the type of computing being done. But this is the dark horse in the race, is these types of probabilistic thermal computers. But this could also just be a scam, right? Like 50-50 chance extropic is just basically like quantum computing, which is just, it's not a scam that it's like fake, but it's a scam in that like they're always perpetually 10 years away. So I don't know. We'll see if they actually manage to solve something or whether they just kind of scam VCs out of money for another decade and then eventually just disappear. All right. Let's go back to what we were doing. Let's give this person another emoji, you know, let them know that they solved our problem. We were looking at this, and then what are we going to do after this? I think I had some stuff on the README here. So I had some ideas. Bug fix for Mamba on GitHub issues, that we did that. WANB for logging, we did that. WANB for plotting, we did that. GPT-4o versus GPT-4 on loss curves, we did that. Check hyperparams with papers, and then looking through the paper for sweep ideas. Okay, so here are the next steps that we're going to do is we're going to start going through this paper or through this code here and see if there's other hyperparameters here that we can kind of pull out and sweep over, right? Because kind of where we want to get to by the end of this stream is we want to have a sweep that we're going to run. So we're going to run it probably for a couple days on a couple different computers at this small scale, right? We're doing a small scale sweep just to look at the hyperparameter space, figure out a configuration that works, and then if we can find one that seems to work well, then we will go ahead and maybe rent out a larger computer and train a bigger model at that configuration. So right now we have seed and hybrid mode as our two hyperparameters, but we want probably more than that. And I think maybe the first things that make a bunch of sense to me are these D model, head dim, D state, right? Because we kind of just pick these arbitrarily, but there's probably better settings here. So for example, this D state. If we go to the actual Mamba paper here, I think I highlighted it. Yeah, so Mamba 2 performs well, blah, 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 significantly better. But then here you go. Additionally, the importance of the state size, increasing from n equals 16 to n equals 64, and then to n equals 256, consistently improves performance. The larger state allows for more information to be memorized. Okay, so we're at currently n equals 64, but I think we want to turn this into a Mamba D state, and we're going to add that up here. Hybrid mode. There we go. And let's also maybe do a little comment here so we know how to do this. This is going to be, we want to try 16, 64, and then 128. So we're not going to go as big as they did here to 256 because we're still kind of just doing this in the small scale. In fact, actually, probably the better thing to do would be to try this. Let's try 8, 16, and 24. Or 8, 16, and 64. Okay. What's another thing we can try here? Let's see. D model head dim. This one is kind of hard though because this is leading to the bug that we had, right? Where you basically need these to match specifically so that they're divisible by 8. So I think if we mess with those, we're going to get a lot of runs that run into that error. So I probably don't want to mess with these too much. One thing we do want to try is this number of layers 6 here, right? Let's see if we get something different by trying this. We can also probably add or change this as well. So let's do args, and then this will be the transformer. What do we want to call that? Attention, maybe? ATT. N embed. And then we'll also do this one here. Args dot n layers. N layer. Let's add those up there. Mamba state, attention and embed, and number of layers. And for number of layers, let's do something really small. So like 2, 4, then maybe 6, and then maybe 8. How about that? And then attention and embed. Let's do, what did we have this set right now? We can go here. Let's see what it was already set at. It was set at 128. Let's try 64, 128. All right. Let's see what else we can look at here. Empirically, we find that having around 10% of the total numbers being attention performs best. So it seems like there's a little bit of alchemy going on here in terms of like what the actual ratio of attention layers and Mamba layers is. Okay, state dimension for each Mamba layer is set to 128. Is that kind of where we're at? State dimension for the Mamba layer is 128. D model 128. Okay, so that's pretty good. We have that. GELU, we use RMS norm, which we already verified is turned on. We do not use any explicit position encoding, whatever. Hidden dimension 4096 and 56 layers. So, I mean, that's a much higher dimension than we have. But this is also a larger model. This is an 8 billion parameter Mamba model. The one that we're using is basically only 100 million parameters. 56 layers. We have 4, 6, and 8. So it just lets you know that we're doing quite a small thing here. Okay. Batch size of 256. Peak learning rate of 1e-4 and a minimum learning rate of 1e-5. Okay. So what they're talking about here is the learning rate scheduler. So if we actually go, I think Karpamambathy is using, let me see, where is it? Yeah, so here's his learning rate schedule. It's a cosine learning rate schedule, which starts at some max learning rate, goes down to some minimum learning rate, and has a specific amount of warm-up steps, right? So the warm-up, you're going to have a lower learning rate, then you're going to go back, or you're going to go to your max learning rate, and then you're going to kind of decrease down to your minimum learning rate. So max steps and warm-up steps should be a kind of a function of the max steps. So I think the proper way to do this is we're going to do this. We're going to do args.maxsteps time, or actually we don't even need to do that. We can say max steps times some kind of args.warmup frac. Sure, we'll take that. And then we're also going to cast it into an int just to make sure. So let's take this warm-up frac. We'll put it up here. Warm-up fraction 0.1. So the first 10% of training is going to be warm-up. We can do that. We can also try, let's try something like 0.5, maybe 0.1. That's probably fine, right? Just try those two. You don't want to necessarily try too many things because this whole sweep is going to be doing every single permutation and combination of these things, right? So like every time you add 2, you're basically doubling your search space. And this is pretty fast. Like we're just training a little tiny Mamba here, so it's not like it's going to take forever, but we still want to be a little bit mindful of exploding the search space. Okay, min learning rate, max learning rate. So peak learning rate of 1e-4 and minimum learning rate of 1e-5. So you can see here they're actually doing the same thing that Karpamambathy did, where it's just 10% of the max learning rate. So really, we probably only need to fuck with this max learning rate, so let's do that. args.maxlr. And then we will put that back up here. So let's do maxlr 6e -4, and we'll also try 6e -4. Let's also try 1e -4. Just something a little bit. Let's also try something crazy here. Let's try like a 1e -3, right? Something just juiced. Increase the batch size. The batch size. So we're going to be running this on different computers, and the different computers are going to have different amounts of VRAM, right? So in terms of the actual batch size, you want to make sure that it fits in your computer. But the batch that needs to fit in your computer is actually this micro batch size. So where is it? Right here. This micro batch size, this is what actually needs to fit on your computer. So because we're going to have to run this on different computers, we're going to want to be able to toggle this as an argument. So we're going to have to, let's come here and let's do args.micro batch size. And we're going to do that, and then we're going to come up here, and we're going to add the micro batch size. This is almost like here. So these are going to be like computer specific, right? There we go. Micro batch size. And these are going to be tuned per computer. So tuned for a specific GPU. Versus these are like kind of more other, you know? These don't matter. These you can change them regardless of the computer that you're using. Let's also do, let's add the actual batch size here. So add argument batch size. Oh, little mistake by Copilot here, but that's fine. Let's go back up to here. Total batch size equals the length of training data set times train config max sequence length. Like, do we want that? Because I think the problem is if we make this, Karpamambathy was like basically calculating this by hand, but like if we turn this into a hyperparameter, then we're gonna have to get rid of all his other weird code that we had here, right? Do we want to do this? I'm like starting to second doubt whether we want to be messing with these. How to stand out from the crowd while preparing for interviews. I don't know if I have good advice for that. I think it's like because different people that are interviewing you are going to care about different things. You know, sometimes you're going to go into an interview and the guy has a programming background and the only thing he cares about is like your programming ability. So like if you sound like you know what you're doing when it comes to coding, they're going to want to hire you. And then sometimes you go into an interview and the guy who's interviewing you is kind of more from like a math background and they're asking you these theory questions and really they want to see if your understanding of the theory is good, right? And you don't really know that beforehand. So it's a little bit of kind of like a luck game. You kind of have to just interview at a bunch of different places, and then if you just keep rolling that dice over and over and over again, eventually you're going to get into a room with an interviewer who is looking for someone that has the exact kind of skill set that you have. And then there you go. So it's not necessarily, it's kind of like a numbers game. You just have to get into a lot of interviews and then you'll get better and better. Grok isn't even using TSMC. They're avoiding that whole supply chain and some of the most constrained components. Oh shit. Okay. So that's kind of cool. You're saying that they don't even, what are they using instead, though, right? What is Grok? TSMC. US chip fab. So it's using Samsung instead of TSMC. Huh. Grok chooses Samsung over TSMC. That's kind of cool, but that's also that's also why the nanometer is kind of old. Pratyush, can't we use gradient accumulation for proxying large batch sizes even on smaller VRAM machine? Yeah, we are basically doing that, right? So this is the total batch size. This determines the actual batch size when it comes to the optimization algorithm, right? So like your atom W here, your optimizer, wherever it is, this thing, right? This has the batch size for that is this global batch size here. I think he called it, right? Total batch size. The micro batch size is just what your GPU can handle, right? So here's the gradient accumulation here. Val loss accum and then loss accum here. Grad accum steps. Where does this grad accum steps come from? Range grad, where did you get that though? Grad accum steps equals total batch size divided by or modded by B times T times DDP world size. This is like just very specific, right? Because it's like you're dividing this into a series of micro batches, and those micro batches all need to add up to this. So if we start messing with this batch size, it might not be dividable perfectly by this micro batch size, which means that you're going to run into errors, right? So like if you have two different hyperparameters where each of them has different settings, and then the settings don't all work together. So like let's say that you had for example, maybe something here, right? And then this setting only works for this here, and this setting only works for this here. What happens is that when you're going to be searching through this space, you're going to get a lot of failed runs. So a lot of your runs are basically going to fail immediately because they can't, it doesn't even work, right? That's not necessarily a bad thing, but it's not necessarily a great thing either. I think we're just going to keep this like this. I think let's not mess with the actual global batch size here, just because this repo has so much logic specifically for that. Okay. Number of training steps. Let's ablate these a little bit too. Let's try a 500, or 500 is a gross number. Let's not do that. Let's do 256. Let's do 512 and 1024. I think that's good. Okay, so I'm just kind of basing this off this. So you see here how 256 leads us to about here. 512 is about here. And then 1024 is about here, right? So that seems to be where we can stop, right? Really, what you would really want to do here is something like early stopping. So early stopping will look at something like your validation loss or even your training loss, and if it just kind of stays the same for too long, it'll stop that run, right? So it's a way to save a little bit of compute, because if you think about it, kind of once we got to here, we could have stopped this training run, right? We didn't really need to keep going all the way to here. So we were just kind of pushing gradients into a model that was already overfit on this data set. So like all of this training here is basically wasted compute. But it's very difficult to know beforehand exactly when your model is going to kind of get to the point where you should just stop doing that. So, okay. Is that pretty much all the things we want to change? Is there any other hyperparameters? So any other hyperparameters you guys want to ablate here? Small batch size might increase the time to converge. Yeah. Bigger batch sizes are more stable. I've shown this before, but there's this don't increase learning, or don't decrease learning rate, or something like that. Increase batch size. So this is kind of an old paper. but I trust it, right? The idea is that increasing batch size during training is a good idea, right? Let's see. Increasing the learning rate, scaling the batch size. Oh, here we go. One can increase the momentum coefficient, so we should probably fuck with those as well. Let's see what we have right now. So in our optimizer, where's our optimizer? Here it is. Got to go here. There it is, atom. Okay, so boom, you see here? Betas. And then he has a weight decay. Where's the weight decay? Weight decay, weight decay, weight decay. So actually we need to come here, weight decay. Okay, let's mess with this one. Let's do args.weight decay. And we also probably want, the problem with these is these are annoying because we're going to have to do beta 1 and beta 2. So I also think that this paper had the same beta 1s and beta 2s, so we can probably keep those the same. Yeah, 0.9 and 0.95, and a weight decay of 0.1, which is actually the same exact settings that we have here. 0.9, 0.95, and then the weight decay was also 0.1, right? So maybe we don't need to mess with that. Let's just try just to see, right? I'm kind of curious, so we'll do add argument. What are some good values for weight decays? Let's ask both of these guys. What are some good values for weight decay? Let's ask GPT-4, and then let's ask GPT-4o. So our value is 0.1. Let's see what it suggests. Okay, blah, 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 blah. 10 to the negative 5 weight decay seems really small. 10 to the negative 2. Okay. This is the range of values that it's suggesting. What about this? 10 to the negative 4, 10 to the negative 3. Okay, so if anything, it seems like we can go smaller. So let's try to go smaller here. Let's try 0.1, and then we'll try 0.01, and we'll try 0.001. Okay. Gradient clipping threshold. Do we have that in this? Clip. Oop. Clip, no results. What about just this? Here we go. Clip grad norm. So what this is doing here, this is called gradient clipping, and this is basically your gradient step, right? I think I've shown this over and over again, but loss landscape visualization, I think is what it was called. This one? Yeah, where is the actual thing though? Explore. I've shown this before, but it's like a really cool visualization. Wow, this is loading really slow. What is this using? See, my CPU's going crazy right now. Trying to load this fucking visualizer. But okay, so we're doing our optimization, right? We're starting at some point in our weight space, and we are optimizing. So over time, we're basically moving down this weight space, and you can see here actually it got stuck in this little local minima, right? So one thing that we can do is that we can increase the learning rate. It's actually over here in the corner, so you guys can't see it, but you can see here I can increase the learning rate. And when you have a bigger learning rate, the chance that you get stuck in that little minima is not as high. So you could think of each little individual like segment here as basically like one step. So that's basically one gradient step, right? And when you're clipping this gradient step, is you're effectively saying, okay, you can't take a step that's bigger than this, right? So you're basically limiting the kind of amount of movement, and part of that is to avoid something like this. You see how here it like kind of ended up in some weird little part of this hill, and then it just took this giant ass step all the way over here? Imagine if you had clipping and it could only take a little step, so it would have probably ended up here, and then maybe it would have been able to go down here, right? So like gradient clipping changes that. That's really what it's trying to mess with. It prevents, and the reason you do that is because sometimes you're sampling data randomly from your training data set, right? So you're basically sampling from these little types of problems in this case, because our data loader and our problem is for this. And sometimes you're just going to get unlucky and you're going to randomly sample a mini batch of data where it's all the weird examples, right? And the gradient that you get from all the weird examples is probably not in the right direction that you want to eventually go. So by clipping that, you effectively prevent one bad mini batch from messing up your stuff too much. Okay, so why don't we ask GPT, what is a good value for gradient clipping? Let's actually copy this exact torch and then utils clip grad norm. And then let's ask GPT-4. Wow, GPT-4 actually did it faster there. It's definitely slower, but it started faster. Prevent exploding gradients, clipping the gradients. Frequently used is between 0.1 and 5. Typical starting point is 1. Okay, that's basically what we have. That's fine. Smaller models, try 0.5 or 1. For larger models, try 1 to 5. Okay. What about GPT-4? What is GPT-4 telling us? Choosing an appropriate, blah, blah, blah. Optimal value can be very task dependent. Yeah, this is kind of what I was saying, right? Where it's like, it's a lot of your data. It's like how much of, if your data is all like kind of low variance, then you don't need to worry that much about these weird mini batch situations. But if you have kind of weird data like we have here, like I'm kind of afraid of sampling a mini batch that just is a bunch of trash, and you don't really want to push a huge gradient based on that. So clip from 1 to 10, a tighter threshold closer to 1 might be more appropriate. Higher variability. Okay, so kind of what I'm getting here is I kind of want to try 1. I think that's a good idea. So let's come here. Let's do args.gradient. Let's do grad norm. Let's just call it the same thing. Grad norm clip. I think that's a good name for it. And we'll come up here. Grad norm clip. We'll try 1.0. Something small. I want to try 0.1. 0.1 might be like too tiny. Whatever. Whatever. We're fucking trying it. Not really. Let's do 0.6, and then we'll do maybe like a 2.0. I feel like that's probably fine, right? Sri Malaya L2 norm sweet spot is 8.86. So L2 norm, you're talking about the weight decay here? Number of epochs, data augmentation, rotating, scaling, cropping. Yeah, I did have that on my to-do list. So right now we're basically using, it's not actually number of epochs. We're basically just feeding the training data over and over again. We actually kind of just hacked it here. So we're going to a specific number of steps rather than just epochs, right? And another way you could do this is just basically go through this and rewrite this entire for loop so that it uses epochs rather than these kind of micro steps. But I don't want to rewrite all this code, right? Like if you refactoring this, I want to touch this code as little as possible because it's Karpamambathy's code, you know? So that's why I'm not doing epochs, and I'm just keeping his like gradacoom step crap that he had right there. Data augmentation. Yeah, that's another one. So I had that here, reversed flipped examples as data augmentation. So we talked about this yesterday, but data augmentation is basically a way to increase the amount of data that you have, right? And it's very popular in things like image tasks because you can do a lot of different transformations to image without messing up the image, right? So flipping a cat vertically results in a cat. Grayscale cat is still a cat. Noise added to a cat is still a cat. It's not quite the same here, but I think we can probably do some, right? I think I'm going to make an assumption here, but I feel like this is probably a good assumption. We can probably flip these vertically and horizontally and be fine, right? I feel like the way that this task is designed, right, it's like these weird kind of patterns, but I bet you if you flipped it over this middle or you flipped it over the horizontal axis as well, it would probably still be a valid task. I don't know 100%, right? And we have to be careful because it could be the case that we're just like literally fucking it by doing that. But that's kind of where I was going with the data augmentation. I feel like there is probably a way to augment this type of data, and we would probably put that in our data loader right here, right? So not this one. Let's actually delete this one. This is the data loader for the text, the LLM kind of text task that Karpamambathy was doing. We don't actually need that. We just need to use our data loaders now. Right here. Right? So we would have some data augmentation here. Put a little Boolean there, right? And then put that up there. And this is going to be a true false, obviously. And this is going to be a true false. And let's actually go ahead and try to implement that. Let's just try the vertical flip. That's probably the easiest one, right? Flip it 50% of the time. You just randomly flip it. You have to augment the labels too, yeah. So it's augmenting all of it. And I don't even know this is valid, right? It's like technically, like I haven't really like dug super deep into this arc challenge. Like I kind of don't really know if this is a valid type of augmentation, but for something like this it is, right? Like so this is an example, a task where the implicit goal is to count unique objects and select the object that appears most times. So here you see how there's like 3 of these and 2 of these. So this is the input and then this is the output, as you're basically saying, oh, okay, this is the one that has the most. And here you have your 3 examples, right? The way that this task works, they give you 3 examples and then they give you a kind of a fresh one. So it's kind of like an in-context learning kind of task. So, oh, okay, I see. You want me to do that one. So the answer to this is going to be blue cross. Right? If you flip these horizontally, or flip these like we're doing here, it's still a valid example. So you've managed to take this example and turn it into 2 different examples. So your neural net is going to be able to learn from both of those. But we could be shooting ourselves in the foot if there's like ones that you can't do that for. But whatever, we'll put that in there. We'll see if it actually does anything. If not, it could actually hurt us, but we'll see. Okay. So now we have a bunch of hyperparameters, but we need to actually sweep over these, right? And so how are we going to sweep? So let's add these in there. We'll say hyperparams, commit, sync changes, and one naive way of sweeping, which is kind of what I did yesterday, is like this, right? So this is the simplest way of sweeping, is you basically just create a script like this, a little bash script that just runs your training with different configurations. So yesterday I basically had a bunch of these, right? Try with seed 42, maybe you do something like this, right? Seed 44, right? 423, whatever, not hybrid mode, different batch size. But the problem with this type of sweeping is that this is going to be really annoying to type every single one of these, right? It's gonna be like borderline impossible to type all of these, right? So what's going on? Swati B. Okay. It's going to be annoying to type all these permutations into a script like this, so we're going to use an automated kind of script machine. So we're going to close out of that. We're going to close out of this, delete, and we're going to make a new file here, and we're going to call it sweep.py. And there's a bunch of different libraries for doing this. Wanby has its own sweep library, which I actually worked on, but I worked on it enough to know that it's trash. And the actual good one that you want to use is this one, hyperopt. This one is probably the best one. You don't need some of the fancy stuff that they have here, but the basic stuff is what you want, right? So you have some objective function, and then this will allow you to basically define some search space and then sweep over that search space in kind of a programmatic way. And because we already have our stuff here, or the Wanby logging, it's like it'll be logged on Wanby anyways. And I'm pretty sure you can create a sweep post. Yeah, you can take these things here and you can do create sweep. Edit the sweep configuration. From existing runs, we guess good defaults for the value. Oh my god, dude. Configure prior runs. Initialize sweep. See, this is what I'm talking about, dude. This sweep stuff is just so trash. Oh my god, alright. Are we reading docs? Is that what we're fucking doing now? You can't have these. This is the problem. So the way that you do this is that you need to make it an int. So you do like this. Type equals int. And then we're going to basically turn it into a Boolean within our code. And data aug. So these two here. Right, because you see, because it doesn't like this. So we need to go to where we're actually using this and then do this. We need to typecast it into a Boolean. And then same thing with this. We actually don't need to typecast it there. I think Python will automatically say 1 equals true, 0 equals false, but okay. We will create this copy. This is going to be a sweep.yaml. So actually, let's get rid of this sweep.py. We're going to do a new folder, new file. The problem is here we want to run these inside Docker containers. That's the problem. Let me try something here. Let me go back to what I wanted to do. Fuck this sweep. I've already done this before, so let me see if I can find it. I think if we go into my GitHub, I did this for this one, the 2023 Squirrel Prize. I had a sweep.py. There we go. Yeah, this is what I remember. Okay, so let's copy that. I'm gonna put that there. Writer, exit. So you can see here I'm messing the hyperparams and the batch size because those are going to be different for the computers. The way I'm going to run this is one computer is going to have one seed and the different computer is going to have a different seed. And then they're both kind of running the same sweep. So that means that even if they hit the same permutation, which probably doesn't happen because our search space is so broad, at least they're trying it with a different seed. So you get to see a different version of that. Okay. Each episode, we can actually probably call it experiment. So if we go here, let's call it experiment. It's a little bit better of a name. This is the space that we're sweeping over. You see here we're using hyperopt, so we're going to actually have to install hyperopt. Let's go ahead and install hyperopt pip. Ooh. Hyperopt pip. Come here. Hyperopt 0.2. Let's look at the release history. 0.2.7. Let's try that one. Pip install hyperopt 0.2.7. And let's also put it in our Docker file. This is going to be in extras, so we're going to put it here. Okay, it installed it. That seems fine. Windows computer, I don't think we need that. This is some other shit that I had that like kind of deleted, removed things because I was doing, I was tracking all of this with TensorBoard, which means you have to kind of like log all these things, but we don't actually need to log any of this crap anymore. So we can get rid of all of that. You basically only have the seed. We'll do 0, default batch size 2. Now we need to actually delete this and delete that. We don't need any of that. Probably don't need this. Get rid of this. And you see this? This dictionary here is basically saying, okay, learning rate, I want to basically sample uniformly in log space between these. Number of warm-up epochs, I'm going to like hard code the number here. So this is for a previous experiment, right? So I don't really want this. What I want is I want this, copy. Then I'm going to go to GPT. I'm going to hit a new one here, and I'm going to say, I want you to create a hyperparameter search space dictionary for me. This is what it should look like, but this is for a different problem. This is the, these are the arguments for my actual sweep. Can you put them in this dictionary format for me? And then we're going to come over here and we're going to copy this. Okay. So basically we wanted to create this dictionary but with these args. All right. So you see it's actually kind of doing this pretty good. Hybrid mode, data aug, Mamba state, attention, max learning rate, weight decay, gradient norm. All of these are choices, which is fine, you know. Having a discrete search space is generally useful. We're going to copy that, and we're going to paste it. See, and that's the magic of GPT, right? Is that if I did this before ChatGPT, I would have to sit here and like manually create that, and it would have been quite annoying to do that. But now I can just do it in whatever that was, like 5 seconds. Okay, so there's the search space. And layers, warm up, just kind of like double checking for sanity choice here. All right, in the experiment, starting episode, pprint, hyperparameters, that's fine. Create output directory. I don't need to do any of this. Train and validation directory. I don't need to do any of that. Save hyperparameters with a YAML. I don't really need to do that. Convert hyperparameter strings into correct format. I don't need to do that. Okay. Summary writer, train. Okay, this is where we're actually going to be doing our stuff. But we don't actually want to do this. So this is actually calling a Python function, right? But we want to run this in Docker. So I'm going to be looking at a different code base that I made. I think I had a code base where I run Docker from Python. Let me see if I can find it. I think it's called like Gen something, Cano, Jim Hands, Tella, A-Frame, Web Stompy, Distiller. This one. Yeah, so this is a project that I did where I was trying to distill a couple different vision encoders into a single vision encoder, but there's a specific piece of code in here that I want, which is the running of a Docker container inside a Python. Starting training. I want run.py, this thing here. Yeah, this is what I want. Build Docker process, build Docker wait for round. So this was running it in kind of like an evolutionary algorithm as well. Blah, 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 blah. Boom, here we go. Running blank, 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 model file path. So I'm going to copy these lines right here. Train Docker, return code, blah, blah, blah. There we go. Okay, copy. So our sweep.py is just going to run Docker containers. And the reason you do this is so that you don't get any kind of leftover effects, right? Like if you just run a bunch of Python functions like this, sometimes your Python will get in a weird fucked up state, and then every single run after that is poisoned and doesn't work well and like is messed up. There's some like allocated memory that you never got rid of, right? So a way around that is to basically just run everything in these Docker containers so that if the run fails and it ends up in some weird out of memory situation, the entire Docker container just gets thrown away. And then you start the next run in a new Docker container. So it basically cleans up any crap that your run could have done. So we're going to get rid of this. We don't need any of this crap here. Score. We're going to need a score at the very end. This is the hard part. I don't know if I really need the score, right? Turn a negative score. Because really all I want to do is just go around it. Yeah, let's just ignore that for now. Okay. Let's see, let's modify this. First of all, we need to indent it. Shift tab. Running train.py. Do that. Actually, we don't even need that. We don't need this model either. We'll put this in here, so this will kill all the Docker containers, kill everything, remove everything. We should also probably put the Docker build in there as well, but I don't think we need it every time. We're going to need to import subprocess. Creating a grid for hyperparameter sweep. Yeah, that's what I'm doing. Why not click the copy code button? Yeah, I think you're right. I could probably just hit that. I guess I didn't want these, but yeah, you're probably right. It's probably faster to just click that and then paste it. You guys are arguing about whether the data augmentation is necessary or not. Yeah. Not entirely sure. Okay. So we can actually go into our README here, right? And we have the specific Docker command that we are using, and we want to use this one here. So this is the Docker command that we did to ensure that the training works, but you see here, I've added a couple things here. So what I added is this -e. So this is adding my WANB API key as an environment variable inside this process, and it also logs in. So this will basically log into WANB so that our results that are running, our run that is running inside this Docker container actually logs to WANB, which is what we want. So we want this, and we're going to put it in here, right? Most of this is actually going to be the same. So actually, why don't we do this and see Docker run --rm. Let's also put in, I don't think we need the -it. Let's actually not put that in there. --GPUs, all. You can also do device 0. This is like specifically the device, but both of the machines that I'm going to be running this on only have one GPU. -v model file path source model. I think we want to do this. PWD into source. We don't need these ones. We need this -e, so let's put that in there. Oh, perfect. Why is this not? I don't know if this will work. I think we have to like literally pipe it in ourselves, but Karpamambathy, so this is the name of the Docker container. We're going to put that in there. And then we have the actual command. So this is going to be WANB login and here's where we're going to put the Python 3. So then we get rid of this. We have Python. Let's do Python 3. And then we're going to have, in our case, it's going to be train.py. And here is where we put all the hyperparameters. So we have args.seed, and then we also want the batch size, or micro batch size. Micro batch size. And here we're actually just calling it batch size here. Let's actually also just call it batch. Right here, sorry. And here it's called micro batch size because in our training script, we're actually, it's called micro batch size. Okay. I think we could probably get rid of this, and I think Copilot should be able to populate the rest of this. Okay, that's it. That must be it. All right. So now we can get rid of this. We are opening up a subprocess. That subprocess is running our training inside a Docker container. You see here some errors because this is not an F string. That. Then we're going to wait on this Docker process to finish, right? So either it errors out or it outputs something, right? So there's the error out. Return code not equals 0. Best scores model equals 0. Let's you see this is the way that we were doing it before. It looks for a specific result file, right? Because the problem with this is that this is going to be running inside a Docker container. So this Python process can't talk to this Python process, right? So we need to communicate the final value that we're going to get here, right? The final value that we care about, which is going to be the very last val loss, this one here, right? That's really what we want because the val loss is this here, right? Let's go to this one. See right there, that's the value that we want the optimizer, the hyperparameter optimizer to look at. So we're going to have to basically write this to a file. Let's say write out val loss to YAML file. Let's call it results. And then we'll do val loss. It's just a little dictionary here. We can actually, I don't want the accum. Yeah, actually that is what I want. Val loss accum.item. Val loss accum.item. And we're going to need to import YAML here as well. So I don't really like this. I don't like having imports like halfway through the code, but that is something that Karpamambathy seems to be doing. Like he puts these imports right here. So I don't know. We're just gonna do that. So that's going to create this results.yaml. It's going to write val loss in there. So whenever we're sweeping, if something happens and the model has some kind of error, right? Error occurred when training. We don't necessarily care too much about that, but we want to make sure that when we keep track of our best scores, I don't even think we need the best scores because I think we're just going to return the score. So we can get rid of this. And this is a minimizer, right? So you see it's minimizing. So it's trying to minimize something. So in our case, it's a validation loss. So we do want to minimize that. So sometimes your eval is accuracy, in which case you want to maximize the accuracy, which means minimizing the negative. So in our case, it's just fine. We just do best val. Actually, let's just do this, val loss. And here we're going to say val loss equals, let's just say some big number here. Let's do 10. You can be fancy and say like inf or something like that, but like, fuck that, dude. That's just confusing. Let's just say 10. Okay, success, training completed, success. Go to this f string. The results file path. This is going to be results.yaml. And the reason this is going to be here is because we mounted this volume here, right? So whenever you do this -v in Docker, what you're basically telling it is you're saying, okay, this fake computer that I have here, I want to have, the source directory in that fake computer to match the directory where I'm running this in. So like if this Docker container writes anything to this source directory, which it's going to be doing here, right? When it writes this, actually we don't need this logdir, it's just going to be just results.yaml. So we can just do this. And actually, if you want to be even more clean about this, what you can do is this. You can say dash data, or let's call it dash results, or let's call it logs, something like that, dash logs. And then we're going to have to make this, so we're going to have to go into our Docker file, and we're going to have to say run make dir dash log. So now we're going to create this log file here, or this log directory inside our Docker file, and then we're going to mount it when we run this. So we're going to say -v, and we're going to say dash logs. Jesus Christ. Oh. I'll get it right eventually, right? Okay, so it'll put it in there so that when we actually get to here, we can look at this like that. Safe load. Okay, get rid of this best score bullshit. Get rid of this. Results. And like that. Okay. And there you go. Get rid of that. So now we got a pretty nice little pipeline there. Max number of evals, this is just how many it's going to run, and then you have the random number generator for that, which is also going to impact basically the permutations of that, which you want to be different, right? You want your different computers to be trying different versions of this. Why is this complaining? It's complaining because it's not starting experiment. Okay, and I think that's pretty much what we want. We can get rid of UUID. Pretty good. All right, let's try that. We're going to call this sweep. All right, I haven't actually looked at the comments in a second. Let me see. I don't think that PWD works. That's a shell expansion thing. Yeah, I'm not 100% sure either. I feel like this won't work either. But we're going to try it out. So we're going to come here. We don't need this to be this big. Let's do this. And we're going to say Python 3 sweep. Actually, let's build the Docker container first. So where's our command to build? It's right here. It's going to... You see, whenever you build a Docker container, it caches a lot of this. But because we changed this line right here, it's going to start from here. So you see how it basically started from the pip install wandb. So whenever you create Docker containers, you want to be careful to order it in such a way where like you're not necessarily changing this shit up here very much so that you don't need to wait too long to build these containers. But yeah, I'm a little bit concerned about this as well. Actually, we should just call it log, not logs. Right? Because then it'll match this little log dir that we have there. To be extra Karpamambathy-like. You know, Karpamambathy didn't say logs, he said log. So you save yourself one character there. And let's actually Control-C this because we're going to have to run it again anyways. I think here's what we can do. I think we can do this. Like that. I don't even remember these commands anymore, to be honest. We're going to go into Karpamambathy Mamba. We're just going to run a Python here just to make sure. Get CWD. Okay, that's what we want. We want this. Like that. And here, we're going to do the same thing. So this will basically kind of hard code it. We have to be careful that we run this always in the right directory now, but it should be fine. Okay, now let's Python 3 sweep.py. Namespace has no attribute batch size. Okay, so because we didn't call it batch size anymore, we called it batch. So sweep.line 117. You can also Control-G 117. That's the cool kid way to do it. Sometimes people do that. They're like all about like going to the direct line, but the problem with that is that you have to move your hands and then type in the number of the line, and a lot of times, like especially if you don't have very long files, I feel like it's easier just to scroll. I don't know. That's all I got. All right, you see that? They're failing. Okay, let's see what they're failing at. Error occurred when training. wandb log not found. Okay, it doesn't like this wandb log. I don't even know if we need to necessarily do this. Let's see if we don't do this. What else? What other failures did we get here? wandb login not found. wandb login not found. Can we just do this? Actually, let's see if we can do it without wandb login. I'm not 100% sure if we need that. We might need it. Okay, fail, fail, fail. Let's see what these failures are. WANB init exception occur. Okay, so it is running into an error with WANB. Let's fucking WANB login. WANB login and Python 3. Let's delete the WANB folder here. Let's see if it actually populated with anything. No, okay, so none of those were getting logged anyways. Jesus. Jesus. God, this is so much more difficult to look at. Cannot kill container, blah, blah, blah. WANB login not found. So let's just sanity check this. Let's run this container and we're going to bash into it. Okay. So we're going to come here. We're going to go like this. Let's actually get rid of this dash practice here. This is actually a bug. We're going to go like this. Copy. We're going to paste that. And we're not going to run anything. We're just going to bash into it. So now we're in it. Right? If we do WANB login, that works fine. WANB login and Python 3 train.py. Detected dubious ownership? What? To add an exception to this directory? What the fuck is this? You see, it's like an error with a dependency of WANB. All right, do we trust this bullshit? Let's just trust this bullshit. We're going to put that in our Docker file. We're going to trust that in there. Let's just run it in here. Run WANB login, and then also run this weird shit here. Okay. Let's Docker PS. Okay, we want to make sure that we don't have too many Docker containers here. This is just the latest one. Okay, that's fine. All right, now let's build this again. And now we're gonna add these things in there. It's not working because we don't have the API key, so we can't actually add that in there. That's true. Fucking annoying. Okay, now let's try to do our little bash. Now we're in here. Now let's do the, let's just try Python 3 run or train. Ah, you see, we didn't actually need the login at all. It's already there. CUDA out of memory. Okay, perfect. That's fine. This actually greatly simplifies our life because we don't need this bullshit here. It automatically, once you put the API key in there, there's some code in WANB that will find it for you, which is perfect because I think this was really not happy about this WANB login. Okay. It's also, let me see, let me check. What do you think about Photon OS? Outdated or good? I don't actually know what Photon OS is. Let me see. Photon OS. Project Photon. Linux-based, open source, security hardened, enterprise-grade appliance operating system. x86, ARM64. Got a bunch of people working on it. I mean, I don't know, maybe, sure. I'm sure it's like cool. Let's see how many GitHub stars they got. 3K GitHub stars. Let's get them one more. Linux container host. So it's basically just like a custom. But like, what problem are they solving? secure, like, you know what I'm saying? Like, what the fuck does that mean? Security hardened? All right. Ooh, real-time kernel, that's something. Especially if you are running like a robot. So like when you try to run stuff for robots, the difference between a real-time kernel and a non-real-time kernel can matter a lot, right? Especially if you're like reading sensor information, reading camera information. But we don't really need that for this, right? Like we don't need a real-time kernel for this. We're just literally running like Python scripts. I don't know. It could be cool. I don't know much about it, but it looks kind of cool. I generally support OS, open source stuff. You are not using Copilot. I am using Copilot. There is a Copilot here. Right here. The problem is that I don't think this Copilot is not GPT, like it's not good. Like it's not the same as GPT-4 or GPT-4o. Like the stuff you get here, I think is better than the stuff you get with Copilot. Copilot is useful for the autocomplete. Like right here, you remember how I was kind of just doing this, and then I go like this, and then it auto-completes, right? So like that's pretty good because I don't have to type it, right? I used to have to type all this shit, and it was take longer, but I don't like the like in features, right? Like the built-in kind of like chat interface here with the VS Code. I just feel like I don't get the same quality that I get just using the web tool or the web version. Okay. So now that we've fixed that, let's run our Python 3 suite. Oh my god, dude, Wanby errors everywhere. Dude, so much bullshit. Starting experiment, CUDA. Error while calling Wanby. Wanby API user is not logged in. Dude, what the fuck? This is literally what we were running. Oh, wait. It's probably this. This is probably not right. So we need to do this. We need to do F os.environ, which is a environment variable. That'll find the Wanby API key for us, and it'll put it in there. Okay, now let's try. Oh, there you go. Currently logged in. Training. All right, guys, we're doing stuff. We're doing stuff. The first one here failed. But that's fine. You know, some of them are going to fail. Some of these permutations, some of these combinations and permutations of these things are probably going to error out. Right? Let's see what this is doing. So this is currently using about 9 gigs. So we can probably jack up the batch size here. So this right here, which is the micro batch size. Let's try Python sweep batch equals 8. So a little bit bigger. Come on, run. Oh, it's because it's not Python. There you go. Using device CUDA. CUDA out of memory. Fuck. All right, one of those was out of memory. And not all of these are going to run out of memory, right? Why is this one? Error occurred when training. CUDA out of memory. Also CUDA out of memory. Also CUDA out of memory. We can look at this. You see 18 gigs. 20 gigs. 23. It seems like we're kind of accumulating crap here. You see 24 gigs. Can we do Docker PS? We just have one of these going. That's fine. I'm kind of a little bit concerned why it doesn't go back to 0. Let's put a breakpoint here so that every time we run this process, it breaks. We should see the memory drop when that happens. Okay, so we're going to run it in here. Python debugger. Okay, we're here. I don't like this. See, that should not be the case. Technically, if we run this, right? Like, what the fuck is taking all that? Oh, no, it's 2 gigs. Sorry. I was reading this wrong. One index wrong. So this is fine. This is 2 gigs out of 24. Those 2 gigs are basically just the stuff that we have running right here. Why don't we also do this? Why don't we also do a watch-n 0.5 Docker PS? So this will basically show us the Docker containers that are running so that we can see it while it's sweeping. Okay. All right, so now we run this one. Run it. So you see now we got one of these running. Vigilant Wozniak. It's going to go up to about 15 gigs. That shouldn't be an I think we should not be getting an here. And there you go. All right, so that one worked fine. So it's up for 28 seconds. 100% GPU utilization, but it's really just because it's just churning really quickly, right? It's like kind of mashing through these batches because the training data set is not very big, but it's technically not using all of our GPU. Okay, one thing we're gonna do here, we're gonna Control-C, and also we should probably go back to Wanby here because there's probably a ton of crap. Yeah, you see all these craps here? 8 seconds, all the way, like, this is all just trash. So let's delete this trash here. Ooh, give me all of these. Is there no way to select all of this crap? Then we're gonna trash. Okay, you wanna clean up your runs. You know, you don't wanna have a bunch of crap just sitting there. But that's pretty much it, guys. We have our stuff running. We can do a little bit more debugging here. So one thing that you can do here is this max steps here. You see how this is 800? That means that we're gonna have to wait. So like we're gonna have to wait a long time for this to basically go through all those steps. So an easier and faster way of doing this is just to make it a really small amount of steps. So let's do something like 16, right? So by setting this at 16, actually we don't really want to do it here because then we're gonna have to rebuild the Docker container. But by setting that at, actually, let's go here. Let's do -- max steps equals 16. So this is going to allow us to go very quickly through so we can kind of see if the whole pipeline is working, right? Because really we want to just test to make sure that this sweep script runs. Okay, so there's the first one. There's no Docker containers. That's good. We're at 2 gigs. That's good. Blast. Okay, we've got 1 Docker container. The training should be relatively quick because it's really only running for 16 steps. Maybe even 16 steps is too long. Each step is about 6,000. Yeah, let's not do that. This is too slow. Control-Shift-2. Let's do max steps equals 2. Let's come here. That's should be annoying. We should have a kind of like a closeout, but that's why we have this here, right? So it kills all the stuff that's running. Let's run this. Docker stats has watch inbuilt. Oh, shit. Dude, that's fucking sick. Thank you, Snooks. See that? You learn shit every day. All right, so now it's going to go through step 0, step 1, step 2. Now it should exit out, and we should see a file. It should create a file in our log called ruh-roh. Why is it on step 3? Step 4. What is going on here? Maxed. Oh, it's because we're overwriting it here. Okay. Close out of that. Comment this one out. Let's move this one down here just so it's simple. And let's also put a little comment here. Debug. So it's obvious for people in the future to know that if you're debugging, you want to set max steps to 2. All right, Control Save. CPU utilization. This even gives us memory utilization. CPU, like, this is really nice. Dude, fuck yes. Okay, let's run this. Okay, the first one failed. Something happened. Second one. This one's probably going to fail. You see how big this is? Oh my god, the computer's lagging out. 15, 24. Okay, there it did 2 steps. Boom. No such file or directory. Logs, it should be log results. So log, and then there should be a results.yaml, and there it is. Okay. So you see that? So we just had this slightly wrong here. It needed to be log. If we actually ran it now, it would work. Control-Shift-2. Control-Save. Let's delete all this shit in here. Just so we have a fresh one. We should also probably delete this every time. So like before we actually do this, let's os.rmdir. Not rmdir, is there like a clean dir or something like that? Clean? So ask GPT. GPT definitely knows this. How do I remove a file at a location with Python OS? os.remove. os.remove. I should have known. There you go. Okay. Does this fail? If it is there like a fail okay? Okay, we'll see if it complains. There's nothing in there right now, so if it fail, it might fail and say like, I don't know what the fuck that is. I can't find it. Okay, there it is. We'll do this. Let's be more formal about this. Let's do this. We'll do result file path. File path. This is going to be a string. We're going to do that. Then we're going to come here and we're going to say if os.path.exists, and we're going to do the log results file path, then remove it. And down here, open up that. Okay, let's run it. Okay, there you go. Validation loss. Go, step 0. Give me step 1. Step 1. And then it wrote it out. Here it is. Oh, it didn't write it out. What happened? ¿Qué pasó? Oh, it's because it keeps deleting it. Okay. That makes sense. We're getting here. It's writing it. It reads it, but then it very quickly deletes it. That's why we're like, it seems to us like it just doesn't exist. So if we put a breakpoint right here, it'll break on that, and now we should be able to see it. It's not there. Row. We got issues. We got issues. Best loss 0 8 point. So it did get it. Error occurred while training. Mat 1, Mat 2 shapes. You see, this is the type of shit that I'm talking about, where it's like there's some specific combination here of this D state, the attention embedding, the end layers. Like if you like, sometimes there's certain combinations of those that don't work, but it's fine if they error out. Wait, decay, val loss, error occurred. What same error? So when is this error occurring? This one worked fine. Success. Val loss 9.8. Okay. I think we're pretty much good, guys. I think at this point we just basically run this overnight, and we go to my other computer, which we don't have to do anything in, right? Because we literally already did the Docker container. So all we got to do is just SSH into it and then just run the sweep, and then we're good. Pretty cool. I don't know. Let me answer some questions here. And why is the learning rate increasing? Is that your sweep? No, it's the warm up. So cosine learning rate schedule. There's different types. There's like cosine annealing is this thing here where you're like going up and down and up and down. But the cosine schedule that Karpamambathy uses is like this one. It's just like basically starts here and then goes down. But this part here, this is the warm up. So you basically start with a small learning rate and then get bigger. And I already closed out of the thing. But part of it is that like whenever you start off, the model is in a really weird part of the weight space, right? Like the settings are kind of weird because we're literally training this from scratch. And so like those first couple batches are effectively just going to be trash. So you don't really want to be pushing a huge gradient on the first couple batches because your model is confused, right? It just like literally woke up. It has no idea what's going on. Like this data doesn't make any sense. So like you kind of want to give it a couple steps before you start pushing larger gradients. That's kind of my anthropomorphized explanation as to why warm-up works. Part 3. Yeah, maybe I do a part 3. I don't know. Maybe I just run this experiment and then I'll post the results on the Discord. Maybe we do another part of this later on. I don't know. We'll see what happens. But again, it's like, even if this worked, even if I ran this experiment, there's no version of this that's actually going to be useful to anybody, right? Like at the end of the day, it's like I'm training these tiny little models on a relatively tiny GPU at home. You know, it's like it's never, in order to even get to this type of shit, it's like you need to be at like a different level of scale. You know, it's kind of like if you build a car or if you do some kind of robotics project in your home, it's like that's not going to be anywhere near the quality of like a Tesla Optimus, right? It's like a completely different kind of league. But the purpose of you building a robot at home is not for you to even try to compete with Tesla Optimus. It's just for you to learn, right? So like it's the same kind of thing here. It's like the point of this for me was to just, hey, just kind of like sit around, do a little sweep, do some Docker, you know, like just get a little bit more practice. Like sit here, think about what gradient norm clipping is, like look at some values and some papers. It's more just like exercising and like, you know, doing a little bit of intellectual exercise, you know, like just getting more comfortable with all of these different tools rather than necessarily being like, okay, if we don't beat the current state of the art, this is all a failure, you know, like that's kind of not the mindset that you want to have, because if you have that mindset, you're just always going to be disappointed because you're never going to compete with these guys. These guys, it's like, not only is this a team of like 12 people, but they also have probably 1,000 times more compute than I have. So if I just have my two little computers and they're just sitting there and they're just pushing these little gradients and running these sweeps, and I come here and I have a cool little like plot, that's a win to me, you know? Yeah. Am I open to do consulting or on explainability? I'm kind of, my work stream is already pretty packed. I have a lot of shit to do, so I'm not necessarily available for much work. But if you ask me maybe later in the year, you know, maybe I have some time. Are my other containers off? I think they're all dead now. Yeah, so they're all gone. Let's actually commit this real quick. Docker file, simplified. Here's the sweep. And there's the train. Let's also add instructions on the README for how to run this. So W Control P README right here. So sweeping. Python 3 sweep.py. That's all you need to run, and then I guess dash seed to 43. What's the answer to the universe one again? Hitchhiker's Guide Answer to Universe. I think it's like 42. Okay, there we go, 42. All right, we got it. Karpamambathy chose a different one. He chose LEET 1337, which is short for LEET, which is short for elite. So that's like a 4 levels deep of internet references. Cool. Let's save that. Sweeping plus commit sync changes. We're good to go, guys. I think we're gonna end it there. I don't know. I'm tired. But maybe we come back to this. Check hyperparams with papers. Looking through paper for sweep ideas. Pad a separate token. Fuck, we forgot about this. We did do this. Let's fix the pad token real quick. So one issue that I realized here that we were doing is that the examples are not all the same size, and we're padding them. Right, so right here, pad sequence, and we pad them with zeros, but a 0 actually technically means something in this task here, right? So 0 is actually the black element here, so basically it has some meaning in this task. I think it'd probably be better if we had a new token, right? If we went here, we increased our vocabulary size to 11, 12. Let's do 12, right? And then we, instead of padding with the 0, we pad with the something else, right? So this token. So np.zeros. Can we just set padded to empty token? We're going to say 11 or something like 10. And we can also do this. np.add or np.array. We're going to add a new separator token. So we're going to have two different tokens here. We're going to have basically the 10 tokens for this task. Then we're going to have an extra token that's going to be the pad token. And then we're going to have an extra token that's going to be basically the separator token. So it lets the model know that, like, okay, this is the end of the input, this is the end of the output, something like that, you know? Something like that. It's kind of like the end of sequence, beginning of sequence kind of thing. We're probably also going to have to increase, I think that's fine, 1049.6. But, all right, that was the last thing. What else did I have here? SSH into the other computer. I feel like we can probably skip that. Weave in distillation. Oh, this was kind of a crazy idea that I had. Like, Another thing that we could, right, so the problem right now is that we're training from scratch only on these 400 examples, which is basically just overfit city, right? Like we're effectively like, there's no way we don't overfit on this giant 400, or not giant, but tiny data set with a model that has even the capacity that ours has, which I think it's like 124, it's like 100 million parameters. I think that really, if we want to make progress on this ARC challenge, we have to bring in extra data, right? And one way to bring in extra data is through pre-training, right? So when you're taking a model that has been pre-trained on a different task, or potentially even fine-tuned, or potentially you're distilling from a model, then there's going to be intelligence there that's going to help us. And I think transformers are general pattern matching. Yeah. So this was a paper that came out that I think is really interesting to think about, because they basically take the ARC challenge and they use a pre-trained LLM for it, and LLMs are capable of autoregressively completing complex token sequences from this. So basically, even though the LLM has never been trained on this type of task, right, it has some general kind of pattern matching kind of skill, right, just from text only, that it can zero shot quite well to these type of things. So rather than doing what we're doing now, which is a very kind of like 2017, 2018 kind of mindset where we're like training from scratch on the data set, we should probably be using a pre-trained language model and then fine-tuning it on this data set. A different way of doing that, right? Because if we use a pre-trained one, then we'd have to basically make sure that all of our model was the exact same kind of size and all that crap as this one, right? If we were doing that, we probably wouldn't be using Karpamambathy's training script. We probably wouldn't be starting from here. We'd probably be starting from something like this and then just making an ARC challenge data set and then feeding it into this. That would be the way to do this if you want to do that. But a different way to do that is with model distillation. Model distillation is, rather than starting from a pre-trained model and then fine-tuning it on your custom data set, you can distill an arbitrary model into your model, right? So this model has some model architecture, and you can take some other pre-trained model, and then distillation models is basically this, right? Where you're saying, okay, you take a big model, in this case it would be the pre-trained Phi 3, or the Samba 3, which is trained on Slim Pajama, which is a giant text data set, right? And then you distill it into our little model. So we would basically take Phi 3 and distill it into this little model, and then we would take our little model and train it on the ARC challenge, right? And you would probably want to actually do something a little bit more clever, where like the distillation works kind of in tandem with the ARC challenge. So initially you're only distilling, and then you start feeding in some batches of the ARC challenge, and then you start increasing the proportion of the batches that are from the ARC challenge versus the distillation. So I don't know, that's kind of the next level I would take this project, but it's a lot of work. Thanks for the stream, I appreciate it. Got a few get a few shot baseline. Yeah, I mean, we haven't even evaluated this on the actual challenge. I don't know how to actually do that. Like, how do you, because I think he keeps the actual test separate, right? Doesn't he have like a secret test set? So like, how do you actually submit this for eval? Like, does he have some kind of like API where you can like I don't understand how you would actually evaluate this. Like, I'm assuming there has to be some kind of service that he provides that's running on his computer that allows you to run eval on like the actual secret test set. But I don't know. We're also doing exactly what he doesn't. Look at this. He says specifically to not do what we're doing. Let me see if I can find it. Yeah, look at this. Do not leak information from the evaluation set into your algorithm. That's fine. We're not doing that. But, e.g., by looking at the evaluation task yourself, or by repeatedly modifying an algorithm while using its evaluation score as feedback, And then we're just like sitting here. What are we doing? Well, actually, we're looking at the evaluation score, and we're basically choosing hyperparameters that give us the best evaluation score. So technically, what we're doing here by hyperparameter sweeping is repeatedly modifying an algorithm while using its evaluation score as feedback, which is technically illegal according to Cholet. So really, we're breaking the laws. All right. I'm tired. I'm tired, guys. I got to go do stuff. Thanks for hanging out. Thanks, everybody. Thanks, Godbuddy, Tomcat, Tarun, Pratyush, Wool, Snooks, Emily, Chabi, Aries, Swati B, JC5000, Razan, Il Kelfelson, I still never know how to say your name, MWD, Brian, Noah, AM, Sarah, Majetti, Oma, and Aries. Thanks, everybody, for hanging out. Hope you had a fun weekend. See you guys later. And, yeah.